Welcome to the second class of this nonlinear vibration of module 3. So, in this class we will continue the solution procedure of the nonlinear equations, and in the previous class we have reviewed or we know about what is a solution or equilibrium points, types of equilibrium points, representation of the solution and how solution of a nonlinear and linear systems differ and how to determine the solution. So, in the last class I told you to determine this solution. So, we can apply or we can go for a qualitative analysis or we can have this quantitative analysis. So, in case of the qualitative analysis, we have seen how to plot the phase portrait to find the response of the system, and also to find the equilibrium points. Let us take few more examples, and let us see how these equilibrium points are determined. For example, so let us take this example. We have a equation x double dot plus x minus 0.1 x q equal to 0. So, as told before, in case of the equilibrium position or in case of the equilibrium solution, so if it is steady state solution, then it will not be a function of time. So, this x double dot or any function of any variation of x with times would be neglected. So, in this case we can neglect this x double dot equal to put x double dot equal to 0, and the remaining thing we can write as x minus 0.1 x q equal to 0, and this will give rise to x into 1 minus 0.1 x square equal to 0, or so in this case we can have this x either x equal to 0 or this 1 minus 0.1 x square equal to 0, which will give rise to x square equal to 10 or x equal to plus minus 3.1627. So, in this case we have 3 values of this x. So, these 3 are the equilibrium position for this equation. So, in this equation x equal to 0 refers to the trivial solution and x equal to plus minus this 3.1627 are the non-trivial solution of the system. So, one can use this qualitative analysis procedure to find the phase portrait of this equation, and one can check whether these points correspond to this center, saddle point, and one can find the separatrix also in this case. So, let us take another example. So, in this case let us take this equation in this form x double dot minus x plus 0.1 x q equal to 0. So, in the previous case this is similar to this doping equation with a subtending type of spring with cubic nonlinearity, that is we have this minus 0.1 x cube, and in this case we have taken a equation where this linear stiffness part is written as negative. So, in this case for this steady state solution, this x double dot will be equal to 0, and this equation can be written as, so x minus 0.1 x cube equal to 0. So, we can have the solution x or x into 1 minus, so x into 1 minus 0.1 x square equal to 0, or we can have x equal to 0 and x equal to plus minus 3.1627. So, in this case also we have same solution, that is x equal to 0 is a solution and x equal to plus minus 3.1627 another 2 solutions. So, these are the equilibrium points of this equation. So, let us take another example. So, in this case, so let us take the example 3. So, in this case u double dot plus omega 0 square u equal to epsilon into u dot minus, let me take this u cube. So, in this case, for steady state one can put this u dot and u double dot equal to 0. So, by putting u dot and u double dot equal to 0. So, one can obtain the equilibrium solution as omega 0 square u equal to 0 or u equal to 0. So, this u equal to 0 represent the equilibrium solution in this case. So, one can obtain. So, this is the van der Pol equation and the previous two equations are Duffing equations, and one can obtain the response of the system by using qualitative analysis or quantitative analysis, and today class we will see how we can use a straightforward expansion method for finding the solution of the system. Also one can go for this numerical analysis method, or numerically one can solve these equations to obtain the solution of the system. And let us take another example in which one has to plot this potential, or one has to do the qualitative analysis for a simple pendulum. So, in case of the simple pendulum the equation can be given. So, in case of a simple pendulum the equation motion of this. So, this has a mass m, and so the system has a mass m and this length is L. So, the equation motion can be written as theta. So, if it is moving with theta, this equation is theta double dot plus omega square sin theta equal to 0. So, where omega square equal to g by L. So, g is acceleration due to gravity and L is the length of the simple pendulum. So, in this case, so if one do this qualitative analysis, so here one can find this f theta equal to, that is the potential function, equal to integration of this f u du. So, that means integration of this omega square sin theta d theta. So, that thing can be written in this form. So, omega square cos theta. So, the equation can be written by integrating this equation. Already we know that it can be written in this form. So, half theta dot square plus f theta will be equal to h, or one can write this equation, or one can write this theta dot equal to root over 2 into h minus omega square cos phi. Here one may note that unlike in case of single degree of freedom system, when we are taking sin theta equal to theta, here one can take this, instead of taking sin theta equal to theta, one can expand, or one can take it directly, and one can find this expression for theta dot equal to 2 into h minus omega square cos theta. So, for different value of h, so one can plot this flow, that is theta dot, and one can find the equilibrium position. For example, in this case the equilibrium position, one can have two equilibrium position. One, so by putting this theta double dot equal to 0, the equilibrium position correspond to sin theta equal to 0. So, sin theta, so this correspond to sin theta equal to 0. So, in this case sin theta equal to 0 at theta equal to 0 and 180 degree, and so one can have two positions. So, this is one equilibrium position and the other equilibrium position will be this one. So, one can have two equilibrium position, one correspond to theta equal to 0 and other correspond to theta equal to pi. So, it may be, so when we will study the stability analysis, or when we will carry out the stability analysis of the system, we can see that this equilibrium position is a stable equilibrium position, while the other equilibrium position is an unstable equilibrium position. So, this equilibrium position represent, in the absence of this damping, so this will represent a center and the motion will be periodic. So, one can have a periodic motion, but this equilibrium position will be an unstable saddle point. So, one can plot this theta dot versus this theta to qualitatively analyze the flow or trajectory of the system, and one can do this last class several methods have been pointed out which can be used for solving this nonlinear equation motion. So, these methods include the straightforward expansion method, harmonic balance method, Lin-State-Poincare method, method of averaging, method of multiple scales, intrinsic harmonic balance method, generalized harmonic balance method, multiple time scale harmonic balance method and modified Lin-State-Poincare method. And before studying this straightforward expansion method, let us study about the numerical methods. By using the numerical method, we can find the solution of these equations. So, in case of the numerical method, let us take this Runge-Kutta method for Runge-Kutta fourth order method for finding the solution. So, in this case, in case of the Runge-Kutta method, so one can solve this initial value problem dy by dx in this form dy by dx equal to f x y, where y a equal to y 0 and this a will be within a and b. So, this dy by dx, while solving this equation dy by dx equal to f x y. So, it has 4 steps. So, one can find the k plus 1th solution as a function of kth solution as follows. So, y k plus 1 will be equal to y k plus k 1 plus 2 k 2 plus 2 k 3 plus k 4 by 6, where k equal to h into function of x k and y k. So, in this case, this k 2 can be written as h into f x k plus h by 2 y k plus k 1 by 2. So, this function evaluated at x k plus h by 2 and y k plus k 1 by 2 will be used to find this k 2, constant k 2. Similarly, constant k 3 can be found by putting this or evaluating this function at x k plus h by 2 and y k plus k by 2, k 2 by 2. So, this is k 2 and this is k 1 and this k 4 also can be obtained. So, by using this k 1, k 2, k 3, k 4 in this equation, so one can evaluate this y k plus 1 as a function of y k and one can find the solution of any governing equation of motion, any differential equation motion, or one can develop a code using this MATLAB to find the response. So, in MATLAB a function ODE45 one may use to solve these equations. So, these equation may be one can solve a linear equation or nonlinear equations. So, one can write a simple code in MATLAB to find this. So, here let us use this equation or use this MATLAB function to solve this linear equation first. So, let us solve this equation m x double dot plus k x plus c x dot equal to f sin or cos omega t, f sin omega t. So, in this case, for a given value of m, k, c and f and omega, one can find x. So, first one has to reduce this equation, this second order equation to a set of first order equation. So, after reducing this equation to a set of first order equation, one can find its solution. So, to reduce this thing into a set of first order equation, so one can write this equation in this form. So, one can write this equation. Okay, so let me write this equation. So, the equation is m x double dot plus k x plus c x dot equal to f sin omega t. So, one can write this x, let one put this x dot equal to z 2 and x equal to z 1. So, if one substitute x equal to z 1 and x dot equal to z 2, then this equation can be written in this form. So, x dot equal to z 2, or one can write this x double dot equal to f sin omega t minus k x minus C x dot. So, this thing can be written this x double dot as x dot is written Z2. So, this x double dot equal to d Z2 by dt. So, this is d Z2 by dt. So, this will be equal to, so d Z2 by dt will be equal to f sin omega t minus k. So, for x one put this equal to Z1 minus C, for x dot one put it Z2. Or this equation also can be written in the form x double dot plus omega n square x plus 2 zeta omega n x equal to f by m sin omega t. This f by m can be written in this form. So, x double dot plus omega n square x plus 2 zeta omega n x equal to f sin omega t. So, by substituting this x equal to Z1 and x dot equal to Z2. So, one can get two differential equation, first order differential equation. The first differential equation is this one, that means d Z1 by, so first differential equation equal to d Z1 by dt equal to Z2, and second equation becomes d Z2 by dt. So, this becomes f sin omega t minus omega n square x minus 2 zeta omega n x dot. So, by putting these two equation in a function, so here in MATLAB this function is written as VDP. So, function dz equal to VDP dz, and using this global value, this for this w represent this omega n, and this zeta f is the amplitude of the excitation, and omega om is the frequency of this excitation. So, by putting this as global variable, so one can write dz equal to 0. So, initially as we have two equations, so we can put it zeros to 1. So, dz1 equal to z2, this is the first equation, and the second equation is written dz2 by dt as dz2 equal to f sin omega t minus 2 zeta omega z2 minus omega square z1. So, using this function one can use this function in this ODE 45, this is the command for finding this thing. So, Tz equal to omega ODE 45 VDP. So, by taking this initial condition, so one can take the time step and initial condition and find the response of the system. So, taking it 0 to 100 time step and 0 to 1 as the initial condition. So, one can find the response. So, n equal to, by putting this n equal to size t. So, here, so three cases have been solved. One first case by taking m equal to 20, k equal to 500, f equal to 10 and omega equal to 8. So, the response have been found for the underdamped case by taking zeta equal to 0.02, critically damped case zeta equal to 1 and zeta equal to 1.5 for the overdamped case. So, the response curves have been plotted both in phase portrait and time response. So, let us see this thing. So, for a underdamped case, one can see the initial part which represent the transient part of the response. So, it is varying with the initial condition and it decreases and finally, it approaches a steady state response. So, this is the steady state response reached after several time steps. So, one can find the steady state response by using this method also. So, this is the transient part, this is the steady state part and this shows the time response of the system. So, one can find the time response for the critically damped case. So, this represent the critically damped case. So, here the displacement in meter and time in second. Similarly, one can find the response for the overdamped case. and if one plot the phase portrait, so this phase portrait is plotted along with the transient part, that is why it shows both transient and the steady state response part. This curve shows the steady state part and starting from a initial condition. So, they show the both transient and steady state part for this damped condition and for the critically damped condition. So, this response this phase portrait represent the phase portrait for the critical damped case and this represent for the under damped case. Okay. So, let us see 3 more examples. So, in this case instead of taking a single forcing function, if one take 2 forcing function. So, this is a 2 frequency excitation case. So, in this case one can note that this x double dot plus 4 x plus 0.2 x dot, here this 4 is the omega n square. So, omega n equal to 2. So, the natural frequency of the system equal to 2 and in this case it is subjected to a excitation with a frequency 2 and 4 and with amplitude 5. In the second example, so it is subjected to a frequency of 3 and 3 root 2 and in the third example it is subjected to a frequency of 1 and 0.99. So, in the first case one expect to have 2 periodic response, one corresponding to this 2t and other one corresponding to the 4, one corresponding to omega equal to 2 and other correspond to omega equal to 4. But in the second case as the ratios are irrational number, so that means 3 root 2 by 3 equal to root 2. So, one can get a quasi periodic response in the solution. In the third case the response will be aperiodic or one can get a beating type of response as the frequencies are very near to each other. So, this is 1 and this is 0.99. So, one has a beating frequency of 0.01. So, by using this Runge-Kutta method the response have been plotted. So, in the 3 cases it has been plotted. So, this is the phase portrait and time response. So, quasi periodic response and so this is the phase portrait for the quasi periodic response and this is the response for the beating type of beating phenomena. This shows the constructive and destructive interference type of things and when one has frequency nearly equal to. So, the beating frequency is 0.1. So, this shows the response and one can find the amplitude, maximum amplitude and minimum amplitude in this case. So, by using this method, this Runge-Kutta method, one can find the time response phase portrait of the system. So, in addition to finding this equation of the linear system, one can use the same equation for the nonlinear case also. So, let us take the doping equation. So, in case of the doping equation, so x double dot plus let us take a equation in this form x double dot plus omega 0 square x plus 2 zeta omega n x dot plus alpha x q, let it is equal to f sin omega t. So, in this case, so one can write those two functions, that is d z 1 equal to z 2 and the second equation d z 2, one can write this in this form. So, it will be f sin omega t minus omega 0 square z 1 minus 2 zeta omega n z 2 minus alpha z 1 cube. But it may be noted that in this case, as one can have multiple solutions, unlike in case of the linear system what we have seen before. So, it depends on the initial condition what we are supplying to the system. So, while solving, so depending on the different initial conditions, so one can have different phase portraits and different time response of the system. So, later when we will study about different resonance conditions, and then we will know that this equation will have many different types of solution depending on the resonance conditions, and for that matter for a particular value of forcing frequency omega, for a particular value of forcing frequency omega, as it has several solutions. So, one can plot the phase portrait in which taking different initial conditions, one can have the equilibrium positions. So, one can find the equilibrium position. So, by using this Runge-Kutta method, so one can find the steady state solution, and as it has several solutions. So, depending on the initial condition, it will go to a particular solution. So, this plot which shows the variation of the trajectories depending on the initial conditions are known as basin of attraction. Basin of attraction. So, by plotting this basin of attraction, so one can find the trajectory starting from a particular point and ending at a equilibrium position. So, this basin of attraction, there are several methods to plot this basin of attraction. So, which we will study in later module, but one may note that the methods may be a point to point mapping method, point to point mapping, or cell to cell mapping method. So, one can use either a point to point mapping method or cell to cell mapping method to plot this basin of attraction for a nonlinear system to find all the equilibrium positions. So, later we will see how to solve this equation by using this Runge-Kutta method, and qualitatively already we have seen one example of the Duffing equation to plot the phase portrait and to study the phase portrait. Also graphically there are several methods available to study this phase portrait. So, one such method is the method of isocline. So, in case of method of isocline, so one can, let us see the method of isocline, and so there are several methods. So, one method is method of isocline, second method is delta method, then we can have the modified delta method, and we can have the double delta method. So, today class we will see about this isocline method, and then we will study the straightforward expansion method. So, in case of method of isocline, iso means similar or equal. So, isocline method, one has to plot lines with equal slopes and draw the phase portrait. So, let us consider this equation u double dot plus omega square u equal to f u u dot and t. So, in this case by taking v equal to du by dt. So, one can write this u double dot equal to d by dt of u dot. So, this is equal to dv by dt equal to, one can write this is equal to dv by du into du by dt, and as we are taking this du by dt equal to v. So, one can write this u double dot equal to v into dv by du. So, by taking this equation or substituting this equation in the first equation, one can write v du by dt equal to f u u dot t minus omega square u, or this dv by du equal to f u u dot t minus omega square u by v. As dv by du represent the slope of the trajectory in the phase portrait. So, one can plot this phase portrait in uv plane, and one can find the phase portrait. So, for example, let us take the equation u, simple linear equation u double dot plus u equal to 0. So, in this case one can write this equation in this form. For u double dot, one can write this is equal to v into du by v into dv by du. So, v into dv by du plus u equal to 0, or one can write this v dv by du equal to minus u by v. So, now by taking different value of dv by du, so if one take this dv by, for example, if one take this dv by du equal to 1, so then this will be equal to u by v, or if one plot this curve u by v, so let this is v and this is u. So, this represent a curve, u v. So, this represent a straight line with 135 degree slope. So, it makes an angle 135 degree with the u axis. Similarly, one can take different value of this dv by du and plot several lines. So, let one take this dv by du equal to minus 1. So, in that case this will be a line with 45 degree. Similarly, by taking 3 by 2, that means dv by du equal to 1.5. So, one can get another line. So, this way one has to, in this method one has to draw several lines, and so this represent, so when v, this represent v equal to, so this is v equal to 0, v equal to 0, or by putting this dv by du equal to infinity. So, this line represent, so the first line what we have plotted with 135 degree. So, then this is dv by du. So, dv by du equal to 1. So, this is dv by du equal to minus 1, and this represent this dv by du equal to infinity. So, after getting these curves now, so for example, taking this dv by du equal to 1. So, this represent u equal to minus v. Now, one can find, now one can draw several lines. So, on this curve draw several equispaced lines with a slope dv by du equal to, so this dv by du equal to 1. So, by drawing several lines with slope equal to 1, so one can draw several lines. 1 means, so it will make the slope will make 45 degree with this u axis. So, one can draw this way. Similarly, for this line one can draw, so as dv by du equal to infinity, so it will come in a straight way. So, this way one can fill this curve with equidistant spaced lines with the slope given by, or the slope taken here. So, by putting these lines, so now by starting at a point, so let us start at a point this. So, let us start at a point P which represent, okay, so some initial condition for which this u and v are given, let u and v. So, let this is 5 0. So, then one can find the next point. So, this curve will start here, and if one has several lines, then one can have a curve, one can obtain the phase portrait. So, by joining these lines. So, in this case actually this should be, this should represent a circle with, so this should represent a circle with radius OP, because in this equation v du by dv by du plus u equal to 0. So, one can write this v dv. So, v, this represent v dv plus u du equal to 0, u du equal to 0, or by integrating this thing one can get. So, by integrating one can, by integrating this equation v dv plus integration v du. So, one get a constant. So, this or one get a constant. Let us write the constant as c. So, this is v square, or one can write this equation v square plus, so this is u v square plus u square equal to r square. So, in this case where r is a constant, so in this case r equal to 5. So, by using this method one can, by using this method of isocline, so one can find the phase portrait of this system. So, after finding this phase portrait one can find the time and then plot the response of the system. So, to find the time one can take, let us take this one quadrant of this and divide this phase portrait, that is v and u, into several steps. So, by taking several steps, let at, so this is at u, so u, so this represent u 0. So, this is u 0, that is initial condition. So, u 0, so at, so one has to find what is the time period or what is the time, or with time how this response varies. So, to plot this y versus t to get the time response. So, one has to plot this u versus time. So, for that purpose one should know what is this time. So, this time can be obtained from this equation. So, one can find this time from this equation, dv by du equal to minus u by v, or one can get this v equal to du by dt. So, as v equal to du by dt and the slope is known. So, one can find this time. So, this time will be equal to this h by v. So, by taking this average velocity as v, or for this from this to this taking this velocity as v 1. So, it will be h by v 1. So, for this, so the time will be equal to h by v 1 plus h by v 2. So, in this way one can find this time. So, after finding time, so as one knows what is the position, that is u, so one can plot this curve. So, in this particular case, so it will follow the sinusoidal curve, that is y equal to or u equal to a sin omega t plus b cos omega t. So, this is the method of isocline. So, later we will study the method delta method and double delta method or modified delta method, and today class now we will study about the straightforward expansion method to find the response of the system. So, in case of the straightforward expansion, as pointed out in the last class, so in case of the straightforward expansion method, let us take this equation x double dot plus alpha 1 x plus alpha 2 x square plus alpha 3 x cube equal to 0. So, one can put this bookkeeping parameter, or one can use this bookkeeping parameter to write this equation also. So, in that case one can use some bookkeeping parameter to represent the nonlinearity of the system. So, in this case let us take this alpha 1 equal to omega 0 square. So, by taking this alpha 1 equal to omega 0 square, and one can expand this equation, or one can write this response x, which is a function of time t. T is the variable and epsilon is the parameter, that is why one use the semicolon instead of a comma. So, this x t semicolon epsilon, so can be written in this form epsilon x 1 t plus epsilon square x 2 t plus epsilon q x 3 t, and if one expand this thing or one substitute this thing in this equation, so then one can write this x double dot equal to epsilon x 1 double dot plus epsilon square x 2 double dot and plus epsilon q x 3 double dot plus alpha 1 into x plus alpha 2 into the square of these 3 terms. So, one can take higher some more terms also by taking only these 3 terms. So, and expanding this equation one can write this will be epsilon square x 1 square, epsilon fourth x 2 fourth and epsilon to the power 6 x 3 square. So, plus 2 into epsilon q x 1 x 2 plus 2 into epsilon 4th x 1 x 3 and plus 2 into epsilon to the power 5 into x 3 x 2. So, in addition to that, if one take this term, then it will be alpha 3 into the cube term of this equation. So, by substituting this equation in this and ordering of the order of epsilon, so one can find the first equation one can get, that is equal to x 1 double dot plus omega 0 square x 1 equal to 0. So, in the order of epsilon square, one can get the equation x 2 double dot plus omega square x 2 equal to minus alpha 2 x 1 square, and order of epsilon q one can get x double dot plus omega 0 square x 3 equal to minus 2 alpha 2 into x 1 x 2 minus alpha 3 into x 1 cube. So, for a given initial conditions, that is at time t equal to 0. So, if it is given that the steady state response, so this is equal to S 0 equal to A 0 cos beta 0, because one can find for this order of epsilon. So, the solution of this equation one can write x 1 equal to, so one can write the solution equal to A cos omega 0 t plus phi, or A cos omega 0 t plus A sin omega 0 t, where A and B. So, A cos omega 0 t plus B sin omega 0 t, or one can write this equation in this form using another constant, that is C cos omega 0 t plus phi. So, as it is a second order differential equation, so one can has two constant. So, either one can use this constant A b, or one can use the constant C and phi. So, both these constant can be obtained from this initial condition. So, for the given initial condition, one can substitute it in this equation and find this A and B or C and phi. So, the solution, so there are two procedure one can adopt. In the first case, one can use, so there are two procedure. In the first case, one can substitute the initial condition first and find the coefficient A and B, and then proceed for the order of epsilon square, or in the second case one can find or substitute this initial condition after finding all the solutions by first taking this equation, and instead of finding this initial condition, substitute this equation in the order of epsilon square and order of epsilon q, and at last find these coefficients or find these constants. So, one can use either the first procedure, in which in the first stage itself one can find these constant A and B or C and phi, or in the second case one can find these constant at the end condition. So, one can, it can be shown that in both the cases one can obtain same solutions for this equation. So, one can have this initial condition this way, and one can write this x 1 0 equal to A 0 cos beta 0, and x dot 0 equal to minus omega 0 A 0 sin beta 0, and the higher order term, that is x 2 0 equal to 0, and x n dot 0 equal to 0 by putting this n equal to n greater than 2. For n greater than 2, one can take this and one can substitute these two equation in this order of epsilon. So, after taking these equation, one can substitute this equation in the order of epsilon square and order of epsilon q to find the solution. So, the general solution in this case, one can find the general solution can be written in this form x 1 equal to A cos omega 0 t plus beta, and this x 2 double dot plus omega 0 square x 2 can be written as minus alpha 2 A square cos square omega 0 t plus beta. So, which will be equal to minus half alpha 2 A square into 1 plus this cos square can be written in this form 1 plus cos 2 omega 0 t plus 2 beta. So, x2 can be so by taking this thing which depends on the initial condition a and beta. So, one can find the particular integral of the other part. So, one can find the particular solution of this equation. So, the particular solution of this equation can be written either in this form or in this form. So, one can write this particular integral x 2 of this equation by putting this thing cos. So, this is constant part. So, this is minus 1 by 2 alpha 2 a square. So, plus minus 1 by 2 alpha 2 a square into cos 2 omega 0 t plus 2 beta. So, for this part one can write the solution to be alpha 2 a 0 square by 6 omega 0 square into cos 2 omega 0 t plus 2 beta 0 minus 3 plus for the other part it can be written plus a 2 into cos omega 0 t plus beta 2. So, instead of writing this constant a 2 beta 2, one can follow the other procedure to write this x 2 in this form. Instead of writing a 0 a 2. So, one can directly write this is equal to alpha 2 a square by 6 omega 0 square into cos 2 omega 0 t plus 2 beta minus 3. So, in the final stage one can find this a and beta, or in the first stage one can, after finding this one can substitute it in this equation and one can obtain. So, the final expression for x one can find in this form. So, epsilon a 0 cos omega 0 t beta 0 plus epsilon square alpha 0 a 0 square alpha 2 by 6 omega 0 square cos 2 omega 0 t plus 2 beta 0 minus 3 plus a 2 cos omega 0 t plus beta 2 minus plus. So, this is order of epsilon q, and neglecting this order of epsilon q one can have this equation, or one can write this same equation in this form, that is equal to epsilon a cos omega 0 t plus beta plus epsilon square a square alpha square by 6 omega 0 square into cos 2 omega 0 t plus 2 beta minus 3. So, either one using this first one can write this equation, using the second one can write this equation. So, writing these equations. So, now taking this a equal to a plus epsilon a 2 and beta equal to, so a equal to a 1 plus epsilon a 2 and beta equal to b 0 plus epsilon b 1 this. So, this way then one can write this epsilon a cos omega 0 t plus beta equal to. So, one can expand this equation in this form. So, one can write this epsilon. So, this will be epsilon a 1 plus epsilon square a 2 into, so this term. So, by substituting this equation one can write this equation. So, where one can further modify this equation and find these things. So, by substituting those equations one can find this, and substituting in the third equation one can write this equation in this form x 3 double dot plus omega 0 square x 3 equal to alpha 2 square a q by 3 omega 0 square into cos 3 cos omega 0 t plus beta minus cos omega 0 t plus beta into cos 2 omega 0 t plus 2 beta minus alpha 3 a q cos q omega 0 t plus beta, so equal to, so this will be equal to, so these terms. But it may be noted that in this equation, so any particular solution of this equation, so because it contains a term 3 into cos omega 0 t plus beta. So, the equation x 3 double dot plus omega 0 square x 3 which contain a function which contain a term. So, which is, let me put some f. So, this is cos omega 0 t plus beta, as this is omega 0 and this is omega 0 square. So, it will lead to resonance condition, and the particular solution of this part will contain a term which will increase with time. But in actual case we have observed that the solution is bounded, but by doing this straightforward expansion method. So, we have seen the solution is unbounded as it varies with time, but in actual qualitative analysis one can find a center in this case, while the straightforward expansion method is showing the response to be increasing. So, the straightforward method is not giving this correct result in this case. So, this is due to the fact that the constant or the amplitude response what we have considered, that is A, we have not considered it to be a function of the frequency. A is not varying with frequency, that for that purpose. So, the expansion method what we did is not correct. So, Lindstedt, so he has modified this method, and by taking a frequency dependent amplitude term. So, he has modified this method, and next class we will study that method, that is the Lindstedt-Poincare method for finding the response of the nonlinear equation. So, you can take few exercise problems to solve. So, plot the phase portrait of the equation portrait of the following equation. Following equation using RK4 method. So, in case of RK4 method, directly you can use the equations what is shown, you can develop your own code, or you can use MATLAB to plot this thing. So, let you plot for this one x double dot plus 10 x plus 0.2 x dot equal to 5 sin 3t, then x double dot plus 5 x plus 0.2 x dot plus 0.1 x cube. So, this is Duffing type. So, equal to 5 sin 3t. So, in this case, so this is the nonlinear term added to the previous equation. So, previous linear equation we have plotted, and in this equation we have a nonlinear term 0.1 x cube added to the system. So, by plotting, so you just check with different initial condition. So, what is the response you are getting. So, taking different initial condition, plot this phase portrait. First you take this term, this forcing term equal to 0, and in third you just take a forcing term 10 x plus 0.2 x dot plus 0.1 x cube equal to 5 sin 3t. So, solve these three problems using this RK4 method, then solve the last problem using the straightforward, solve the second problem using the straightforward expansion method. First find the equilibrium point in this case. To find this equilibrium point, put x double dot equal to 0, x dot equal to 0, find x, and then plot the equilibrium points and check with the straightforward expansion method whether you are getting the same equilibrium point or not. So, next class we will study about the Lindstedt-Poincare method. Thank you.